So we've got these three different types of energies here. There are other types of energies we can calculate too, but we're going to look at gravitational, kinetic, and elastic energy. And we're looking at, rather than try to memorize the formula, we're going to see if we can, how much of the formula we can work out. So we've seen that height is going to be related to gravitational energy. It's the higher up something is, the more the more gravitational energy it's going to have. By the way, if it was the other way around, if it was the higher up something is, the lower the gravitational energy, h would be there, but it'd be divided by h. So because it's not that, because height's going to increase, we can see it's not going to be divided. Things are going to be multiplied. So to work out what other things might affect the energy, we've got to think. If something has a lot of gravitational energy, we could convert that, and let's say a ball or rock or whatever fell. If it had a lot of gravitational energy, then it's going to make a bang. So this bottle of water is like a millimeter above the desk. If I let go, it makes a bit of a bang. If I did it a bit higher, it would make a bigger bang. So height is going to affect the energy, because I can measure that energy by just measuring how much sound it makes when I drop it. Now, what other things would affect how much sound, without changing the height? What else could I do to change how much of a bang it would make when I let go? So I can't use the force, because that would be adding another energy to it. I'm talking about releasing the energy that's held within it while it's being raised up. So what other things, so we're just simply letting it go, letting it do what it would naturally like to do. So if a rock fell off a shelf or a top of a mountain or something, then clearly if it fell off a shelf, it's not going to make so much noise. If it fell off the top of a mountain, it's going to make a lot more noise. What else about the rock, besides its height, could cause it to make a bigger bang? That's right. So mass, in other words, we would use the word mass, not weight. So weight is the force. However, it does relate, because sometimes, in fact, this gives us a big clue. I'm going to put the M there. And the thing is let's think about now, why is it that mass why is it that mass, when I lift something up, then it has the energy to be pulled back down again? And are there some planets, now I'm giving a big clue, are there some planets where I could lift the same mass up, the same height, but when it fell, it didn't fall with such force, and therefore it wouldn't produce as much of a bang and so on? So in other words, what would be the third thing that could change the amount of bang it would make when it fell? That's right. So I I gave you quite a big hint. It was so it wasn't the great bit of quite a leading question really, but yes, gravitational field strength. Now, originally you said that it was weight, and I corrected you and I said mass, but actually m times g is weight. So you could rewrite this as just weight times height. And sometimes it is written like that. Not often, to be honest. Nowadays, you pretty much always see it written like that. Weight is mg. We hardly ever use the symbol W nowadays. We just write mg. But yeah, so that would be the equation for gravitational energy, gravitational potential energy, going to be the mass multiplied by gravity, by the strength of gravity, or by the strength of the gravitational field, or the gravitational field strength multiplied by the height. So this little g here often causes people a lot of stress, because they think that's a lot of things to remember. But it's just the strength of the gravitational field. So I can just say gravity, but gravitational field strength. So how strong is a gravitational field, wherever that is? So on Earth, the gravitational field strength, the strength of the gravitational field, is 9.81. So most of the time, most of your questions, G will be equal to 9.81 newtons per kilogram. In other words, every kilogram will feel a force of 9.81 newtons. Now, this is sometimes written as 9.8 newtons per kilogram, or sometimes 10 newtons per kilogram, depending on how much you round it up. And obviously, I could be more accurate than that. It's not exactly 9.81 newtons either. Okay, so that's how we can get around having to remember the gravitational energy equation. Let's have a look at the kinetic energy equation now. We've got clearly velocity is going to be related. It's going to be related to velocity, and in the same way, we're going to use the same sort of idea. Imagine something crashing into a wall, like a car crashing into a wall. If it's moving faster, when it crashes into the wall, it's going to make a bigger bang. What else could we change about the car that would also cause it to make a bigger bang besides the speed? That's right. You can say mass again. So if it was an empty car, empty small car colliding into a wall at 50 miles per hour, compared with a train crashing into a wall at 50 miles per hour, clearly the train is going to make a bigger bang. So mass must be related to it. So the rest of it, we kind of have to just remember it, to be honest with you. So it's actually half times the mass times the velocity squared. The squared bit might help a little bit, because you may just try to remember that the velocity or the speed has a larger effect on the energy than the mass does. So in other words, if we look at this, if we think about this for a moment, if the mass were to double, then the kinetic energy would double. In the same way as the gravitational energy, if the mass doubles, the gravitational energy doubles. But if the velocity doubles, the kinetic energy quadruples. So the kinetic energy is directly proportional to the square of the velocity. In other words, yeah. And whereas you look up here, these are all directly proportional to each other. So if I double the mass, I'll double the energy. Or if I double the gravity, I'll double the energy. Or if I double the height, I would double the energy. So they're all directly proportional. The reason why the half is here is a little bit more complicated. We won't go into that just yet. So there is a little bit of memory really needed there. It is possible to derive it, but we're not going to do this right now. Then we've got elastic energy. So elastic energy, basically, imagine you've got a spring and you've stretched it out, you've applied a force, you've stretched it out. It was that length, and now it has been extended by this length. Symbol used to be X, now they're using E. So E for extension, right? And then L for original length. Extension. Okay, so original length. So what kind of things do you think would affect the amount of gravitational energy inside this stretched spring? Well, if I were to stretch this a lot and let go, it's going to come back with a larger force and make a larger bang again. Basically, that's what I try to think about, is how much of a bang it would make when I allow this potential energy to be released. All these are potential energies, including kinetic energy, by the way. So it doesn't seem like a kinetic potential energy, but it is. Won't go into the reason why in this video. But yeah, so the elastic energy the extension is related. So extension is going to be in the equation. The other thing is similar to the reason why, if we look up over here, that the gravity, similar to like gravitational field. So gravitational field strength is pulling that mass towards the ground with a larger force. So it's like the strength of the gravitational field. And in this way, we're going to have the strength of this spring. So if this spring was really, really thick and really, really hard to stretch, then if I did stretch it and pull it by 10 centimeters and let go, it's going to come back with a larger force. So that's the sort of the strength of the spring. And we call that the spring constant. So I'll put a little comment here. That's the spring constant. And that's basically the strength of the spring, or maybe you could say the stiffness of the spring. It's I should edit that it's I should say that it's measured in Newton per meter. Yeah, so Newton per meter. So in other words, how many newtons would you need to apply to stretch it by 1 meter? That's the spring constant. I think I might just move it just a little bit so you can actually read the K. Right. So, and then the rest of it, again, unfortunately, is a little bit of memory. But the good news is it looks quite similar to the kinetic energy equation. So it's half times the times the spring constant times the extension squared. So, good news is that you get given one of these. I think it's this one you get given, and then you have to just remember, oh, I know the kinetic energy equation looks similar to that. So then just try to remember the order in which the letters go, and it just reduces that load that is expected on your long-term memory. So, so that should help a little bit.